So we're asked to let y be the position in meters of a bus at time x, and x is measured in seconds. The equation that we're given is y is equal to 3x squared plus x. And for part A, we're asked to find the instantaneous velocity at an arbitrary positive time x sub naught. So again, I'm going to draw out the picture of what's going on here. Okay. And so we've got some curve 3x squared plus x, which looks something like this. And we need an arbitrary point here that we need for the instantaneous velocity. That is the same thing as, I should write it like this, slope of the tangent line. Okay, so what we're going to do is down here, I'm going to pick an arbitrary point, call it x naught. Doesn't matter what you call it. You can call it A, B, smiley face, George, doesn't matter. Now what we're going to do is we're going to take another point. Well, first, before I do that, the height of the function, which is this guy right here, at x naught is 3x naught squared plus x naught, right? And that's how this works. So we're going to grab another point off of that, which isn't going to be too far away. We're going to call it x naught plus a little bit. Okay, and now that guy has a height of 3 times x naught plus a little bit squared plus x naught plus a little bit. So what we're going to do is we're going to use those two, and we're going to find the secant line running through them. Well, we're not going to find the whole secant line. We're just going to find the slope of the secant line. So we want the m value, which is the delta y over the delta x. And so the delta y is 3x naught. By the way, the delta y is right here. Okay. So it's going to be 3x naught plus delta x squared plus x naught plus delta x minus this guy down here. So minus 3x naught squared minus x naught. Remember, we have to subtract both these guys off. So what I've just computed here is this length in blue. And now what we're going to do is we're going to put that over the change in x. Well, the change in x is this length here in yellow. And if we do the computation here, it would be x naught plus delta x minus x naught. And look, when you do that, these guys drop out and you're just left with delta x. So no surprise there. So remember, this is just, right now, it's just a secant line. So we'll do our algebra out here, and we get 3 times the quantity, x naught squared, plus 2x naught delta x, plus delta x squared, minus 3x naught squared. Oops, I missed a piece there. I need plus x naught plus delta x, now minus 3x naught squared minus x naught. Okay. Now we'll distribute this 3 in. now we'll see what we can go ahead and cancel. So we've got 3x0 squared on negative 3x0 squared. We've got negative x0 and x0, so these guys are gone. Notice that the only things that are left have a change of x in it, and it's always that way. So this is going to be equal to 6x0 delta x plus 3 delta x squared plus delta x all over delta x. And now we'll factor out a delta x. Okay, and so that gives us delta x. By the way, delta x can't be 0. And the reason for it is if delta x was 0, we'd be finding the slope of just a single point. We can't do that, right? We need 2 points. Because what would happen is if delta x was 0, this point right here would lie on this point right here because there'd be no distance between them here. So we're going to end up with this. Now, this is the secant line. However, we want the tangent line because we want an instantaneous rate of change. So the f prime at x0 is when we let this guy, delta x, get really close to 0. And when delta x gets really close to 0, 3 times a number that's super small is just a number that's super small. So this thing right here basically is nothing, right? And I've said this before, and we'll say it again here. It's like if you had $1 million and someone gave you a penny, you wouldn't care very much about the penny because in the grand scheme of things, it doesn't matter, right? It doesn't impact your income very much at all. Same thing here. This number is even a greater difference than the $1 million and the penny. It's so small compared to these guys that it doesn't matter. So the slope of the tangent line at any x0 value is 6x0 plus 1. Notice that that follows our formula that we're given in this chapter as well. And our formula in the chapter says that you take the a value times 2 times the x0 value and you add the b value. Well, there we go. Now, of course, this is much quicker, right, than doing all this. But this is really what's going on in the background, okay? So we've got this 6x0 plus 1, which is our answer for A. So f prime, the function that tells us the slope of the tangent line at any point x0, whatever we pick for x0. It could be 2, it could be 3, it could be 1.5, it could be 12, it doesn't matter, okay? For any of these guys that we pick, we get 6x0 plus 1, and that tells us the slope. So now answering B is really fairly easy. Okay, it's just a little bit of algebra. I'm gonna actually move it down to the bottom here, and we're gonna do it in yellow. So we want to know when is the velocity 10 meters. So at what x value is this guy equal to 10? So what we want is to know when is this equal to 10. Well, very simple algebra here. We'll move the 1 over and get a 9. Divide each side by 6. So we get 9 over 6. Each of these are divisible by 3. That's 3 over 2. Or 1.5 seconds. So if we take 1.5 and we plug it into here, we would get 6 times 1.5 plus 1, which is 9 plus 1, or 10. So the slope of the tangent line, if I drew that out, here's the guy at 1.5. If I drew in the tangent line, This guy has a slope of 10, and the interpretation of the slope is the rate of change, so that's 10 meters per second. That's it. That's how you work these problems.